series. And I want to get some closure, Ryan, today on this topic of energy balance. But there's one little tidbit I want to point out before I get into the Earth's energy balance. This is a graph. Remember how we said the radiation can go above 1,000 because of reflection from clouds? And that causes all kinds of people to panic about things. This happens to be some data from the Campus Environmental Observatory for last January, but it was a series of days that were partly cloudy. So there's a black line on here that is the calculated radiation for a clear sky. Now this is winter, so note it only goes to about 450 watts per meter squared, but that's the value for the winter. So here's 3 different replicate radiometers in here, and this was partly cloudy, this was partly cloudy, this was very cloudy. Then look at this day right here. The clouds acted like a lens, like we talked about, and even though the clear sky was about 450, we had readings of 650 on the instrument. And that wasn't bad instruments, it was reflection of light by clouds. So sometimes these can go way above clear sky by radiation focusing on them. And then we calculate net and shortwave on here in addition, but the main point here was to show this. But it has been very useful for us to calculate a clear sky radiation, so you can tell here's a day when it was clear sky and the instruments are close to the model. They came up with the sky, came down with the sky. So because the clear sky model is so useful, there's a website that shows this. I can show it on the magnet. Here's the magnet right here. And many of you have this magnet. Boy, they're really bonded together. This is the third and final magnet that we're going to talk about. And this is at clearskycalculator.com. And for any time of day, any point in the world, this calculates the clear sky. And it's particularly accurate at solar noon, and you can use it to tell if your instruments need to be recalibrated. All of our tests with this indicate in the summer at solar noon, this is within 2% of the true value. The coefficients you put in here include humidity and temperature because of atmospheric attenuation, elevation, latitude, of course, time of year. Calculate radiation anywhere in the world. That's just a little tidbit that's been really useful to help people make better measurements for radiation. And it's fairly widely used. I think it could be used a lot more widely for people to make better measurements. So now, this is the outline for today, where we hope to get to. Radiation balance of the Earth. I think it's real interesting. As soon as we get these numbers, we can figure out radiation for a leaf. How's this look if we do the whole planet? And this is I guess I need to, maybe not, don't need to zoom in or out. There it is, the whole planet. There's many diagrams like this, but this is one of my favorites. I stopped into Paul Campbell's office a year ago, and he had this on the wall of his office, and I gave it to him, and he loved it, so we put it on his wall. Here's all the incoming solar energy to the Earth. So 6%, boom, right off the bat, reflected by the atmosphere right back into space. Clouds, this is a variable. If there's more clouds, more reflection, but some clouds. And then finally, Earth's surface, pretty small reflection. Absorbed by the atmosphere a tiny bit, but then finally here's the absorbed by land and oceans, and then this warms up and it re-radiates into space as long wave. radiation. So it's coming in as shortwave, and it's going out as long wave. I love these colors because the burner on a stove glows red, and that's long wave radiation. So all of these are small numbers, but you can see how this is a delicate balance if this radiation balance changes. And for all the apparent controversy about global warming, we know CO2 absorbs long-wave radiation. We know CO2 is going up. We can mathematically calculate the absorption of CO2, of radiation, by CO2 in the air, and calculate the heating caused by that. So you could say, how could this be controversial? These are known physical principles. And as we say, the absorption of long-wave radiation by CO2 is unassailable. We know exactly how it changes this cooling by long-wave radiation. Here's the amazing thing about this. Remember we had, well, you could see them on here. There's not numbers on here. But this is 1,000 watts in the middle of the day coming in. These are big numbers. Here's a paper by a whole bunch of authors. One of the key authors is James Hansen, who was quite famous in circles. He's testified before Congress many times on this, and look at how many authors they put in these papers. But look at this. Our climate model, driven by human-made greenhouse gases, aerosols, calculates the Earth is now absorbing 0.85 watts per meter squared more energy than the sun than it's emitting to space. Less than 1 watt is the energy imbalance of the Earth. Now he puts a plus or minus 0.15. Those are some serious models. You're not saying, oh, this is less than 5%, we'll throw that out. All that stuff matters. So even though these are known physical principles, the energy imbalance is small, but it's enough to cause the temperature to rise. I think the only controversy about global warming is, what's the effect of rising temperature? Yes, it's rising, and yes, it's caused by CO2, and yes, the CO2 is caused by people. So, Canadians have a t-shirt that says, I'm in favor of global warming. So some people, it's not a bad thing to them. And then people say, well, look, it's going to melt the ice caps, raise the ocean, Miami will be flooded. So they can move. There's the controversy. It's not what's happening, it's how serious is the problem. And that's where we get into erratic weather. If all that happened was a slow, steady increase in temperature, a few tenths of a degree per decade, we can deal with that. But if the weather goes chaotic, now we got a big problem. And there's the cutting edge of climate science research is, will global warming cause erratic weather? And there's lots of evidence that it does, but people disagree about how much erratic weather might happen. If it changes rainfall patterns, that's a big deal. That can change agriculture. It can cause a lot famine for a lot of people just by shifts in rainfall patterns. So to me, that's the cutting edge of climate change research. Not whether it's happening, but what are the long-term consequences going to be? But when I read this paper, it was some years ago, but I just about fell out of my chair when I think of the fluxes of these numbers. So I want to go into this a tiny bit more. Several years ago, I'm going to zoom out on this, NASA got ready to launch a satellite called GLORY. And this is a brochure on GLORY, Understanding the Earth's Energy Budget. Now, NASA has lots of satellites doing this already, but this one had specialized instruments to get some of the lesser-known parameters to measure them more accurately. And we were all so excited about this satellite. It took years of work and had really expensive instruments. It blew up on launch. And now we're trying to get money again to launch another version of it. But in this brochure was a 2-page analysis of the Earth's energy budget that I thought was the best short summary I had ever read of this. So I'm sharing it with you. This is, I have 2 handouts. One is the one I just showed, which shows percentages of all these arrows. And now you have a sense of what those arrows all look like on a single leaf. Apply the same principles to the whole planet. This one shows absolute numbers on this. I might be able to focus this a tiny bit better. This one shows absolute numbers. You can't see them here, but they're on this handout. And what's reflected and absorbed. And of course, these numbers change as the Earth rotates. We're not always measuring it right pointed at the sun. There's nighttime in there, and we're on the edges. But in a nutshell, this shows these. So here's another reason, another thing that helps you understand some of the controversy in this. Here's radiative, what's called radiative forcings, which is just another name for what's causing this. And I want to zoom in on this just a little bit. Radiative forcing components. Now this is becoming more and more common for people to express their data like this, but if you haven't seen this before, and people debate the size of the error bars on these, but it also helps you understand the controversy about global warming. So if that bar goes up, that means it's a factor causing the Earth to get warmer. If it goes down, it's a factor causing Earth to get colder. So if there's things on here that reflected radiation, the Earth would cool. And if they absorb, it gets warmer. Here's CO2, the biggest bar in this graph. In the end over here is the net of everything. Here's CO2. That error bar is the difference among the models of what CO2 is doing. And they're not all the same. And this is watts per meter squared. So 1.5, 1.6 watts per meter squared, plus or minus 0.1 or 0.2. That's not very controversial. We understand this. Methane, nitrogen oxide gases, and halocarbons are real powerful absorbers of long-wave radiation. So just traces of these have a big effect, and cumulatively these add about another watt per meter squared. These have been going into the atmosphere before there were people, but human activities have increased these other gases as well. There's a lot of work on methane and nitrogen oxides and other things now in addition to just CO2. So then we go into ozone, and there's tiny elements of cooling and heating. This is a much smaller bar, but a bigger error bar on that. Stratospheric water vapor. Tiny changes in atmospheric water. Water absorbs long-wave radiation, so if the humidity changes, it drives warming, but not very much. Then albedo. If we painted the Earth white, we'd cool it off. Well, land use changes can mean that more radiation gets reflected into space. If we have big forests, they absorb a lot of radiation. We cut them down, we just have bare ground. We reflect more radiation into space. So there's bigger error bars here, but it's plus and minus. Now we get to aerosols. Droplets, tiny droplets of things in the air. If we had a microscope, you could see them, but they're droplets of liquids in the air. They reflect radiation. And look at the size of these error bars. Cloud albedo effect. Those clouds that are causing us complications in our model, if it's cloudy all the time, the Earth is going to cool. So that's one of the huge variables in here is what the clouds do, because look at the size of that error bar. Clouds are aerosols after all, so they're in this category. And then a couple other tiny factors, changes in solar radiation. People said the sun is just putting out more energy. Well, yes it is. There it is. It's above zero. and with a pretty big error bar, but this is not a big effect. We would like to say it's all this, party on, don't worry, these things are minor compared to the sun, but the data doesn't support that hypothesis. And here's the net effect. Now this model shows about 1.6 watts per meter squared, and the paper I just showed had 0.85 watts per meter squared, so you can see where the different models vary a little. But there are no models that say this is 0, and there are no models that say it's a negative number. They just vary in the magnitude of the warming. But this helps explain why it's controversial, because some things make it cooler, some things make it warmer. For years we've worked with NASA on long-term space missions, growing food for people in space. So one of the issues is terraforming Mars. Can't we just start making Mars more of a nicer planet? Well, yeah, but it's cold. Well, we'll just fly some stuff up there that turns it black and makes the planet darker, and then you run the numbers and yeah, that works. You can make Mars a darker color, get the absorption up, it'll start to warm up. It'll melt the water into ice, and pretty soon we start to create an atmosphere up there. So there literally is smart people saying, let's get Mars darker so we can, might take 50, 100 years, but let's get it darker so we can go and live there. And this is these application of energy balance principles to whole planets, not just our own. Whole universe has to follow the first law of thermodynamics. As far as we know, we haven't discovered a universe that doesn't have to follow that. So we take those principles to other places. So with all the conversation and debate about global warming, I think it's useful for people to be a bit more educated, particularly when you get the principles of shortwave and longwave radiation. Now you can take those and apply them to lots of places. So I'm not sure where NASA is on another satellite, but a big part of that one was to do aerosols. This is following up now in my order of my organization on a few little things that we didn't get into. Remember when radiation absorbed equals radiation in times 1 minus albedo. This was all fine, and then we said for a typical leaf, the albedo is 1 minus 0.5. So 0.5. However, here's shortwave radiation again, short and long. Here's the short wave. Here's the long wave. L, S over here. Long wave is really pretty consistent. It doesn't matter what wavelength it is for long wave as far as absorption of materials. Matters a lot for transmission through the atmosphere. But when we talk about long wave radiation, a number that's at 8,000 would behave similarly to 50,000. It's all those wavelengths are the same. This is not true for shortwave radiation. The wavelengths matter a lot for shortwave, and when we say 50% albedo or 25%, when people talk about albedo, they are talking about an average of all the wavelengths. And remember, this is about 280 nanometers to 3,000. This whole thing is in units of nanometers. Lots of times you see this in micrometers. These wavelengths matter a lot. And let me get to this in a second. In the textbook for right here, figure 7.4, this shows for a typical leaf what's absorbed, what's reflected, and what's transmitted. And of course, this is very far from a flat line. You can see that 50% is an average, so that's okay. We can use 50%. But here's photosynthetic radiation, micrometers, 0.4 to 0.7, almost all absorbed. And remember, this is 40% of the total, almost all absorbed of this. This is what causes photosynthesis, so it's a good thing, it's absorbed. Then we get to 700, and there's no more, the chlorophyll molecule does not absorb light past 700. It's just heat. So I'm going to say that plants are pretty smart. They let that thermal radiation go right through, or they reflect it, and this radiation is like 10% absorbed. This near infrared radiation. And if we draw it on our graph right here, we have UV, we have 400 and 700. This is 95% absorbed. This radiation in here. Then suddenly it gets just past that, and I can show this. And this part of it out here is maybe 10% absorbed. It depends on the exact wavelength. You can see this bounces around out here a little. But it's a little misleading. It simplifies the model a great deal to say we just have one number for albedo. But since we're dealing with plants and not just parking lots and other surfaces, it's important to know that these vary a lot. That's the diagram in the book, and lots of people diagram the same thing in different ways. Here's a diagram from another book, and I like this a little better because it's not on a log scale, so you can see it better. And now it has absorption here, photosynthetically active radiation, 400 to 700 nanometers. This is green light. So a little bit more green light bounces off, and a little bit more is transmitted. But boom, right at 700 nanometers, the reflection and transmission go up, and they're real low until we get out here to 1.4, 1.5, and then they become absorbed more. But the amount of radiation is going down like this. So these are huge amounts here, and after we get out here, there's just much less radiation. This shows differential absorption by the leaf of those components. And I could tell you were worried about this because this is the handout from the other day. Let me back off so you see the whole thing here. This is the handout that talked about typical values for albedo and emissivity of these. And then if you kept reading for being in advance, you're itchy to ask me what's going on with these numbers down here. And I think I got to fold this to show it. On the bottom of this is what happens to this radiation. There. And I'll zoom in a bit. But these are typical numbers on the bottom of this. And it segues into longwave too. Photosynthetic, now on here I put 90% absorbed, and over here I put 90%. It's high. It depends on how thick the leaf is, whether it's 90 or 95. Roughly equal amounts of reflection and transmission to 100%. So great, there's photosynthetic. Boom, we draw our line, and it switches to mostly reflection and transmission. And this is a big reason leaves can stay cool. They're not having to absorb that thermal radiation. It's of no value to them, unless they're cold and they want to try and get warmer, but they got plenty of light to keep them warm. So then we go in this to longwave radiation. And 4,000 to 100,000 this says micrometers, and this should say nanometers right here. These are all nanometers. So 96% absorbed of long wave, and we had emissivity and absorptivity of 0.96. Okay, what happens to the other 0.04? If it's not absorbed by the leaf? And the answer is it's reflected. There was a tiny bit of long wave radiation that gets reflected by surfaces. Tinfoil reflects 97% of long wave radiation. So for thermal radiation, tinfoil is just like a mirror. And if we put a piece of tinfoil right here, and I put an infrared gun on it, it wouldn't tell us hardly anything about the temperature of the tinfoil. It would tell us the temperature of the people in the glass, because it's reflecting all the people in here. So this is a tiny number, but when we get into rigorous analysis of energy balance, this 4% matters. And in a field, it's just reflected back into space, but depending on the situation, it can get reabsorbed somewhere. So,
what does it do with it?
If it's reflected, so what does it do with the 4%? If it's reflected, nothing.
The 96%, does it do?
This 96% becomes heat. It's thermal radiation, and it makes the object get hotter until it reaches a new equilibrium. It's converted to heat.
Planck can't utilize it.
No, it can't utilize it. So this is as we said the other day, this is a big reason leaves are warm. But of course, the good news is they can also, by radiation, get rid of it too. But it's highly absorbed, but not completely 100%. So this little example here about emissivity and absorption of reflection leads to the use of some instruments to measure radiation. And the place that I have found that's the most interesting about this is in buildings. All buildings built in the last 10 to 15 years have low E glass. And if you ever dealt with the building, you've heard of low E glass. Have you heard of that, Boston? Right? So what's low E glass? It's all the rage. Oh yes, we're putting low E glass. That is low emissivity glass. The glass looks like tinfoil for long wave radiation. Now exactly the physics of how they're doing that I'm a little fuzzy on, because we could certainly put tinfoil up and it would be very effective. But this glass right here, this is a new building. This has low E glass. I've never tested it. But here is, let's do some research right now about the emissivity of the glass. So here's a little cheap infrared gun. And we got several around here, and I've bought lots of these. And you can get these things for under $25, and it gives you the surface temperature in either Celsius or Fahrenheit. So, and they're remarkably accurate for what they cost. So let's see if I can get this in Celsius so we understand the numbers. So let's do a test right here. I'm getting, and I can't see this, I'm getting 32 Celsius for this glass, and that's probably the temperature of the ceiling up here in this room. Although the glass is pretty warm because the sun's shining on it, 3% of the signal, if this was low, that low E, this is probably not the same as tinfoil. The emissivity might be, let's say it's 10%. The temperature I'm measuring is 10% of the true surface temperature and 90% of the ceiling. So it's warmer than the ceiling, but it's certainly not the temperature of that glass. Now most of the things in here are mean, we could do it on, I don't know if this is low E glass because it's not an exterior wall. But if we did it on this, you can see this has a little red LED, so you can tell where you're pointing. But if that was cold and this was warm, it'd reflect and it'd tell us the temperature in here. That's the concept of low E. And let me try and attempt to take this one step farther. One thing I know for sure, as soon as anybody learns the principles of these stuff, they want to own a lot of instruments to measure it, because then they understand what's going on. So this is a thermal imaging camera. Now these things are 25 bucks, and the more accurate ones cost a few $100s, but this thermal imaging camera, these have come down fast, and $1,000, something like that for this. I mean, they used to be a lot more than that. So now, let's see if we can point, now I don't know if the camera can get this, but we point at this window and it's telling us the glass is warmer than the wall, but mostly the glass it's reflecting the long wave off the wall.
I see your other gun.
Oh yeah.
I'm going to help your demo.
Excellent.
I'll be
Terrific.
right
Oh, you're going to get a, we're going to test some low E. Anyway, here, you can see me in this. What parts of me are hotter than others. These are really useful for refined measurements of different temperatures. The absolute accuracy of these is not the greatest, but the relative accuracy is really impressive. As you can see, tiny changes in temperature. If I get out of the way, we can start to see the windows in this. The board's much cooler. And I could pass this around and you can look through it a bit. I just charged it up, so hopefully it's got enough charge to last for a little bit. But this, if you spend a few minutes with this pointing it at things, it really drives home the principles of long wave radiation and the value of using long wave emissivity to get temperature of things. So I have one more demonstration of low E glass. I went down to Bennett's Glass and I said, don't you guys have a demo of this that helps people understand low E? And they got all excited and they said, yeah, we can order one. So this is for people selling low E glass. This side right here is ordinary glass, and this side over here is low E glass. And like I said, 15 years ago, there was just only primitive low E glass. Now, I think it's almost code. I think everyone has to use low E because it keeps the heat in. You're not going to lose heat by radiation, and it works both ways. The cold radiation outside, it doesn't radiate inside anymore. The cold is reflected on the outside. So now let's start our experiment. Got a light, and these little radiometers spin in proportion to how much radiation is hitting them. And you can see that the ordinary glass is making this spin more than the low E glass. Oh, can this see it too?
Oh, yeah.
Yeah. So there's the principle of low E. These are real cool. You put them in the window and they spin like crazy.
Oh, yeah.
So
This actually works pretty good.
this is for people that really just want to see a demo. They don't understand the physics. They just want to see a demo, and the ordinary glass makes that spin more. Thank you. So how would you calibrate one of these? You can take, this is called a Leslie cube, but it's a cube full of water, and a cone inside painted as black as we can get it. Special flat black paint so that emissivity gets very 0.99 something for the emissivity. And if it's a cone shaped, the long wave bounces back and forth sideways, so the emissivity gets even higher because it's a cone shape. So my assistant has filled this with hot water, and now we could put this right here. What are we saying? I think it holds it.
50.
80?
50. 50 Celsius.
Mm-hmm. Now I want to get close. Let's see if we can. What are we getting there?
51.
Yeah, okay.
Now pointed at the silver side.
Yep, good. So now let's go over here. What do we get there?
31. 31.
It's emissivity. This is a silver side. It's not emitting the heat. I touch it and it feels hot, and they're exactly the same temperature, but because this is such higher emissivity, it gives us a bigger number. You can use these in an instrument. You can use these to determine the field of view, because all these instruments have a cone-shaped field of view, and you would like to think that this little red dot, I'm only getting that red dot, but it's in fact averaging, this one's probably averaging a 2 or 3 meter squared area up there because it's low cost. If you want to get just the red dot, you got to pay more for a more precise instrument. Then you can take these, and if I do this, and it's got a high temperature, and I start to move it back away quite quickly, it'll start to see the edges. And it's no longer measuring just that black cone, because it's averaging the cone plus this. And some of the higher quality instruments, you can go far away and it'll still just see the cone. But that's one of the reasons you pay more for higher end instruments, and you can buy cheap ones like this. Plus, these work pretty good if the temperatures are all within 5 degrees C of the instrument. But if you try to measure a hot surface with this, they're just not very accurate. So that's another problem with radiometers, is they always measure the delta T, because there's always an exchange of radiation between the instrument and the surface, and it measures, says this is my temperature, that surface is 5 degrees warmer, so it adds the two numbers together. So this is emissivity on principles of it, and fortunately glass helps you to see this. We could do all kinds of things with tinfoil in here too, showing how it reflects the radiation like a mirror, and it shows the power and the importance of the emissivity. Two simple equations or laws that relate to radiation that are important. One is Wien's law, and it's pronounced Wien's. This is a German guy. Many years ago, he's looking at the relationship between long-wave and short-wave radiation, and he says as objects get hotter, they radiate at shorter wavelengths. Because this is showing us a dichotomy of short and long, but wait a minute, isn't there stuff here in the middle? Yes, there could be. So Wien's law says, now let's erase this. The maximum wavelength, and in this case this would be this point right here, maximum, equals, no, I'm going to be simpler. It's proportional to 1 over temperature. Real simple. Inversely proportional to temperature. So as the temperature of an object gets hotter, it radiates at shorter and shorter wavelengths. So this is low temperature objects out here. This is the sun right here. And the peak number from the sun is 550. I'm going to put nanometers or micrometers. That's pretty, you could look at the yellow magnet, that's pretty close to that peak wavelength.
It's 0.55 if you're mind.
Yep, thank you. Now that I switched to micrometers, 0.55. Now let's put some numbers in this and solve it. And so now, after we get the concept here, now if we do equal sign, first of all, this is temperature in Kelvin, not in Celsius, and this is the maximum wavelength in micrometers. So now we have units, but it's not 1 over this. This is a constant, and this constant is 2897. So there's the entire Wien's law. Roughly 3,000 divided by the temperature in Kelvin of the object will give us the peak wavelength. So if the sun is radiating at 0.5 micrometers, now we're going to do some math to make this simple. 0.5 micrometers. How hot is the sun? Well, we'll rearrange Wien's law, temperature in Kelvin, and I'm going to put we're going to round that to 300, and this is 0.5 micrometers, rounding. The sun is 6,000 Kelvin, rounding to make the math easy, and that's pretty hot. We don't have anything on the Earth that's that hot, which is why this shortwave is coming from the sun, because it has to be that hot. What if we put, how about the inside of an oven? We're going to bake the turkey. Let's go to let's take this off, and now we're going to say maximum wavelength 3,000. Now we're going to put temperature in here, and you bake a turkey at 400 degrees or a pizza at 400 degrees. That's roughly 200 Kelvin. So the inside of an oven might be 273 plus a couple hundred, 500 Kelvin, to make this math easy. So 6 now I got a mistake in here somewhere. This is coming out to 6 micrometers. Yeah, no, it's not a mistake. So this is 0.5, and a hot oven is out here these are nanometers, so this is 8 micrometers. So a hot oven is over here, 6 micrometers. So this is why terrestrial objects all radiate out in here depending on their temperature. And even a hot oven doesn't get us to shortwave radiation. It's still longwave. These are all described by Wien's law. And there's another application of this. Here is a graph of doing this for a couple of temperatures. So here's 5,500 Kelvin, and as this gets cooler, it shifts out here to longer wavelengths. Not by much, but it shifts. So you see two things happening. Remember Stefan-Boltzmann equation? The total radiation is determined by the temperature. And as the temperature gets cooler, the area under this curve gets less. And as it gets hotter, it becomes more blue. And the hotter the object, the more blue. The cooler the object, the more orange and red. So we use Wien's law, 0.1% of the people in the world know this, to determine color temperatures of lights and all kinds of things. We say in film, this is a 4,000 Kelvin film, and this light is some Kelvin temperature. None of them are smooth curves. It's just an effective way to say the color temperature of objects. We talk about color temperature, but it's from Wien's law. The bigger the number, the more blue the output. Blue lights have, you could say, cool white fluorescent, which is blue, might be a 6,000 Kelvin light. And a warm white fluorescent, which is more orange, might be a 3,000 Kelvin light. And that all comes from Wien's law and this shift from the maximum wavelength. So when you see those color temperatures and you think through this, and anytime it's inversely proportional, you have to shift your thinking a little. Hot objects are more blue. Planck's equation. I don't have my picture of Planck here, but he's one of the top 25 scientists of all time. And this picture, he has a tie on and little tiny glasses, and he just makes it look like he was a very organized guy, and he was. He lived to be 82 years old, which is a real accomplishment in the 1800s when he lived. So we have this refrigerator magnet, which everybody's got on their filing cabinet now. And we're showing this both in photons and energy. And the shape of the curve. And the photon flux is all the physiologists that are modeling and predicting photosynthesis. And the energy flux is all the meteorologists that are modeling temperature and the differences in temperature. They're obviously both important, and they're different shapes. So is there any way to go back and forth between joules? This is per meter squared per second per nanometer. This is meters squared per second nanometer. Is there any way to go back and forth between joules and moles of photons? And the answer is, thanks to Max Planck, and what I do with my black marker. Here it is. Thanks to Max Planck, I'm going to erase some of this to give Planck lots of room for his equation. Another very simple equation. Energy per photon is proportional to 1 over the wavelength. Real similar to this, only this is temperature and quality of the light, and this is helping us go back, allowing us to go back and forth between joules or watts of energy and photons. So energy drives thermal reactions, and photons drive a whole nother set of reactions, like photosynthesis. We know that one photon excites one electron. That's called the Stark-Einstein law, and that's what causes photosynthesis. That is exactly what causes electricity in a solar photovoltaic cell. One photon excites one electron, and we get electricity. Those solar voltaic cells aren't running off of thermal radiation. They need shortwave radiation, and we need to count photons to determine electricity. So we get Planck's equation, inversely proportional to wavelength. Now, if we change this to equals, this 1 becomes h, and c, and c is the speed of light, h is Planck's constant. And I don't have these two numbers memorized, but they're big numbers. And this is joules per photon here. If we put numbers in this, and this is how I remember it, because it's like a lot of things, you work it out for one value, and then you can forever ratio things to that value. But if we do Hc over 550 nanometers. Now this is right in the middle, between 400 and 700. 550 is the average wavelength of light from the sun. It's green light, it's average light. Right in the middle, this comes out to be 217 kilojoules per mole of photons. Putting these numbers in. I'll work out a page with the step-by-step math worked out on this and all the numbers in it, but there's a relationship. So now if you say, what would the energy, what would this number be at 600, well, you can easily ratio this and you get this relationship here. So Planck's equation allows us to go back and forth between energy and moles, and you can keep going with this equation like we have here to 800, 900, 1,000. Here's the photon flux. These photons are longer, associated with longer wavelength. They have less energy. I like to think of the UV photons are really high energy. You know, if this was 315 nanometers, this thing would be, let me see, if we took half of this, 275, this would be over 400 kilojoules per mole. That's ultraviolet light. That's high energy photons, which is why ultraviolet photons are so degrading to everything. They're super high energy. They're just, I don't know, they're like third graders. They just got a lot of energy. And then you get out here to 900 and it's the people with canes and there's low energy. They're still one person, but they're low energy. So these photons past 700 no longer have enough energy to excite electrons for photosynthesis, so we don't count them. And down here, they're too high of energy for photosynthesis. They're damaging. There's not that much down here either, so it's got to be just in this right range. But it leads to the shapes of these curves. Incidentally, solar photovoltaics are, in the laboratory, similar efficiency to photosynthesis. In a good solar voltaics, and now you get up 30–40% efficiency. Photosynthesis can be 30–40% too in the lab. And they're both going off of one photon, excites one electron. One makes carbohydrates and the other one makes electricity. Solar panels can use these photons. They keep absorbing out to 1,000, even 1,100 out here. So solar panels can use some of this longer wave radiation. Photosynthesis can't. And it's generally why solar photovoltaics are more efficient than photosynthesis. They can capture that part.
You said something that, so sunlight, the majority of sunlight tends towards the green spectrum. Plants evolved not using the most plentiful source of sunlight.
Yes, so the question is, how come plants are green? If there's so much green light, wouldn't they want to capture that? Two answers. One, it's not, this is a fairly flat curve, so it's not that much different green light. But still, why don't they absorb everything? Why do they have a dip at all in green light? And if they could capture that green light too, they'd be more efficient. So you could say, well, chlorophyll just doesn't absorb green light, that molecule. Well, then it's a bad molecule. They should have got something else. And the way I like to think of it is, animals came along and they eat plants. And our eyes can see green light better than any other wavelength. If we drew our eyes on here, I can put it on here, green, put it on here in black, blue. Here's our eyes. This is a little thing. Our eyes look like that. We see green really well. We don't see blues and reds very well. So animals evolved to be able to see plants. Plants reflected the green light, and the animals that could see that green light found the plants better and got more food, and maybe, I don't know. I never heard anyone else say that, but that's a good sounding hypothesis. It's interesting, the wavelengths of light reflected by plants are the ones that we see the best. And so, but you could also ask, couldn't we invent a better molecule for plants that captured all this? And now we know there's lots of pigments in plants besides chlorophyll. If you look at older plant physiology textbooks, they say, well, plants don't absorb much green light. Look at chlorophyll. In fact, let me answer that. Let's see. Let's put this right here. We got this done with this. Here's our 400 to 700 blown up big. If you look at a plant physiology textbook, chlorophyll looks like that. It absorbs blues. There's chlorophyll A and B, but they look like this. They absorb blues and reds, but the chlorophyll hardly absorbs any green. And all the plant physiology textbooks said, well, chlorophyll doesn't absorb much green. So guess what? When we invented efficient LEDs that were blues and reds, a whole bunch of people went, wow, these are perfect for plants, because they match the absorption of chlorophyll. There still are no efficient green LEDs. The ones green, we have them, but they're not efficient at all. So they said the LEDs are perfect for plants. They match the absorption of chlorophyll. And then we found out they really don't work very well through 10, 20 years of work. And how come? Well, now we know. And if you take a modern plant physiology textbook, they have curves in here like this, and like this, and they're all colors. I'm out of colors, but you get the idea. There's a whole bunch of curves in those now, and they say multiple pigments absorb all the light. There's a new pigment, psychorethrin, is discovered in algae. I don't know about discovered. It was clarified in algae just a few years ago. Its peak absorption's in green light. So there's the potential to genetically engineer to put more psychorethrin in plants, and then they will get that green light. They won't look green anymore, I guess. They'll look, I don't know, black. But so this is a long answer to an interesting question. How come they don't get pigments to capture every speck of it? And what I would like to see is pigments so they could use some of this. There's a lot of energy right in here. And if we could just get pigments to get out to 800, wow, we could feed the world. But we don't have them. Chlorophyll ends at 700 and then nothing. Yes, they would absorb more heat too, but we'll precision irrigate and save water and get more yield. So why do pigments do what they do? How do they evolve? They're interesting questions. Damon.
So is the limiting factor on plant growth capturing radiation to drive photosynthesis, generally speaking?
So the question is the limiting factor absorbing radiation for yield? And
then if you got additional pigments, you'd be able to grow more, but I don't know that that's...
Yes, it is the limiting factor. When you plant in the spring, you got beautiful light. It's May and early June. There's a lot of light. 90% of it's wasted because it hits the ground. And here's the little nice green plants, but 90% is wasted. Finally, they fill in and yield takes off. So there's an example of absorbed radiation. But what we're talking about here is after it fills in, couldn't we get it? I mean, here's one answer to the question, kind of a smart-ass answer. What do you mean? They already absorbed 95% and you're complaining? Couldn't we get this to 98? And yeah, that would be a 3% and every little bit helps. So, okay. I'm going to stop here and we'll take a break. This is the end of radiation lectures. When we come back in a few minutes, we will talk about transpiration. All of this is we're going to get transpiration by subtraction. Well, can't we just measure it directly? And the answer is sort of. So let's take a break.